Hi everyone, welcome to another Applied Building Science webinar. We're going to give everyone just a couple of minutes before we get started, but while we do that, I'm just going to go over a few housekeeping items if this is your first time. So this is, we're using the GoToWebinar platform. I know that you're using about 6 of these every day, and they all work a little bit differently. So I just want to show everyone that little red arrow there gets hidden sometimes. So make sure you click that. That's going to expand everything. First, you're going to see your audio settings. I'm guessing that you can hear me, so hopefully those are good, but you'll also find the handouts there. And actually today we have our a PDF copy of these slides that you can download. So I know that's always the most popular question is whether or not you can get a copy of the slides, and there they are right there in the handout section. So you can download those, follow along, review them later, whatever you want to do with them. And do keep in mind, as always, this webinar is for a general audience. We've got HERS raters, BPI folks, regular old homeowners, and people like me who don't know anything about the topic today. So some of this is over your head. Just bear with us. I think that we're all going to get quite a bit of education today. So, and as always, send your feedback, send your questions. You can send them through the questions feature that's built into the GoToWebinar. I haven't seen any yet, but hopefully you all are finding that. If you have any comments, there's no chat or anything. We're not going to make you log on to any other website. Just shoot the questions. We'll go to them as we go through the webinar, or we'll hit them at the end, depending on the subject matter. And without further ado, I guess I'll introduce myself. My name is Joey Starr. I'm a technical project manager at Southface. I primarily work in the with our weatherization assistance program. So I do some training there and some other project management as needed. And Mike?
Yeah, hi. Joey, I missed you. It's been a month since we got to do one
Oh,
of these. It seems like a long time. And welcome everybody. And again, if it's your first time, thanks for joining us. And I believe that these do get recorded and hopefully posted. I think we're recording, right?
yes.
Hopefully
Good.
posted.
Thanks for checking. Yes,
All right,
we
check.
are.
And I have some experience with load calculations, and I've taught a class or two on how to do them, but I don't do it every day, so I may be a little rusty, and I definitely had to kind of shake the cobwebs out a little bit. But here's me if I was a Simpsons character. Let's see, are we going to get anything here? There we go. And then Joey, I ran your photo through as well, but you came back as Dr. Zoidberg. So.
Why not Zoidberg?
Anyway, as always, we do appreciate people joining us. And someone told me that our webinars are like the car talk for buildings, except less funny. I added that part, but anyway. Joey, anything about Southface you want to add?
Oh, we're just hoping to get back there at some point. We used to open these with that, and I just don't know if that's going to happen anytime soon. So we do miss everyone. We miss having the classes, but we're happy to still be engaged with the community in these ways through these webinars. So thanks for joining, as always.
And keep checking our website too, because I think we may try to start offering some more virtual classes like DET and things like that. So coming up,
Yeah.
so support us, help us stay alive. And then Joey.
Yeah, and one easy way to do that is to come to Greenprints. So Greenprints is an annual conference, or was it semi-annual? We're gonna do it online this year. So here you can find some information on our website. The entry fee is just $30, and then if you want CEUs, it's a little bit more, I think 45. So it's a very affordable. Come, you're going to see some great panels. Mike, I think you're doing one or two. So if you're not tired of hearing us by now, you can hear us talk about the new Georgia Energy Code. There's some much better panels though. If I were going, I probably wouldn't listen to Energy Code. But so do check that out and come back and join us. I think it's August 6th right there on the script on the
We'll try to
slide.
make ours entertaining though. Ours will definitely have the entertainment factor. And as always, we want to pitch some of the great resources that are available at southface.org under resources, and particularly more recently some Georgia Energy Code stuff, such as the field guide, which has a lot of good pictures and information. As always, we think, building science principles are the foundation of the work that we do here at Southface, and just trying to, really this webinar series has been a lot of fun because we covered the basics of heat, air, moisture. If you haven't seen those, go back and watch them. But then we're getting into specific topics now, and that's been really fun. So, and also I want to ask too, if you have ideas for topics, things that I certainly haven't run out, but if you have suggestions for things you'd like us to cover, I'm gonna pull my mask down here. And we're assuming that you're falling into this category of one of these, and if you're not, chat us up, let us know who are you if you're not listed here. So we're just trying to kind of breeze through this part quickly. And yeah, we make some learning objectives. I always do that so we can ignore them, but we do have some learning objectives. We're gonna basically talk about manual J and make sure you're comfortable with what's sensible, what's latent, which one's hard, which one's easy. Talk about common errors that you find in a load calc, and we'll see what happens from there. I am struggling, Joey, to get my mask off because I'm about to strangle myself. And Joey, you want to kind of talk about heat transfer while I try to untangle myself?
Sure. Yeah, so we've been building on this, and I think this is kind of the culmination of this is when we do load calculations, what we're really trying to find out is how much heat is entering or leaving the home. So it's important to understand the basics of heat transfer, and that it comes in three forms: radiation, conduction, and convection. And we'll talk about each of these as we kind of go along here.
Beautiful. I wish I had my web camera on for that, my video camera on for it was quite comical. Also, as you might imagine, the choice of how we define the thermal envelope for basically three identical houses here can have a big impact on the load, and on and whatever affects the load, of course, affects the operational costs and performance. So we can put a duct system in this place, and in some of these designs it's in an attic, and in some of these designs it's inside the thermal envelope. And I say duct system, I mean the equipment as well. So same for down here. And just again, what is happening in an HVAC system is, in let's say air conditioning mode, we're pulling air that's hot from the house, we're blowing it across a cold refrigerant coil. So we're giving up heat from the air of the house, and then that air is leaving at a cooler, drier temperature, and then that's being put back into the house. And of course, we're catching condensate, liquid water off the side of this and draining it away. And it's all working because of the magic of the refrigeration cycle, which in the summertime, we've got our compressor here that is compressing a gas, and that hot gas is going to an outdoor heat exchanger where we're dumping heat, and that hot gas turns into a liquid. And so anytime you change phase from a gas to a liquid, a whole lot of BTUs, a whole lot of heat is essentially rejected in this case. And then that liquid goes and throttles across a metering device, and then the cold liquid is essentially what goes in the evaporator or indoor coil. And of course, a heat pump does the same thing in the opposite direction. We're going to probably stick mostly with air conditioning mindset since it is the summer. Joey, why do we have an HVAC system? Just so we can talk about refrigerants? What's the purpose of this?
Well, yeah. So what we really are trying to do is keep the temperature, the humidity, and everything inside the home comfortable for those living in it. So it's really important to consider the occupants when you're talking about HVAC. And I believe in an upcoming slide, we talk specifically about the different components of human comfort.
Yes, we do. And then again, very quickly, I think I've kind of covered this, but this is the indoor refrigerant coil. In the summertime mode, in cooling mode, we're gonna have the liquid come in. It's gonna flash across a small orifice, which is a metering device. That's this expansion valve here, and it'll try to regulate the amount of liquid refrigerant that's in the coil. And it's always liquid at the bottom of the coil, and it's always vapor as it leaves the top of the coil. And that's why you have this cold suction line that's insulated up here. And so You know, when we talk about a matched coil or the indoor coil, that's what we're talking about. And matched means that this coil has been tested under AHRI conditions with the outdoor condensing unit. That's the American, I don't know, Home Refrigeration Institute, something like that. And of course, in order to dehumidify air, the other big message is this coil needs to run air across it for a long time because it takes a while for condensate to build up on the fins and drip down and collect in the pan and then drain out. This is the condensate drain right here. So it takes a while for that to happen. And don't you love the window on our indoor coil there? Joey, you mentioned this. You want to talk about it? What affects comfort? Not just temperature, right?
Yeah, so we think of temperature, you know, obviously that's what we see on the thermostat, but it's much deeper than that. Something that's near and dear to our hearts down here in Atlanta, Georgia, is the relative humidity, obviously. So higher humidity levels prevent us from adequately regulating our body temperature through sweat. So that in turn makes it feel more uncomfortable. Also airflow, you know, if you're standing under a fan, that's going to help with that sweating process, and it's going to help you feel a little bit cooler. And of course, fans only really work well if you're standing by them or under them.
Airflow.
Exactly. And then surrounding surface temperature. So this is going back to that kind of radiant heat gain. If you know, the room that I'm in, you know, has an exterior wall that gets pretty hot in the afternoon, so I can usually feel that on my face because that's radiating heat to my body.
Yeah, excellent. And then, you know, just again, another interesting way of looking at the same thing you just talked about. These are sort of the factors that there's, you know, that affect everything you just said. And also, what are you doing in the building? And are you being physically active? Or are you being sort of passive? And I always found it funny that this is an old slide I found of the ASHRAE comfort window, which is basically saying humans are only comfortable in a pretty tight, you know, roughly 10, 12 degree band of temperature. And, you know, it's not the same band in the summer as in the winter. So there's really only like, you know, there's only like one temperature at which you can, and one moisture level where you can kind of keep almost everybody happy. And I say almost everybody because the goal of the ASHRAE standard is only to make 80% of the people happy. So 1 in 5, if you're not happy, that means I've done my job. Too bad. So I think that's kind of funny. Aim low, as I always say. Other factors, of course, we talked about the importance of maintaining good indoor humidity levels. And if you're at room temperature, which is typically in the low mid 70s, and your relative humidity is 50%, that's the sweet spot. That's the best place to be. You're keeping dust mite population at bay by not getting too humid. You keep viruses, you know, they don't love it if it's above 40 and below 60, those kind of things. So, you know, 50% is a great target for us to try to achieve. And then, Joey, you want to take a real quick definition of sensible and latent, because I want to make sure we cover this.
Yeah, so sensible is that kind of room temperature, what you see on the thermostat, whereas latent factors in the relative humidity. So we did quite a bit of work on psychrometrics. I wonder if Mike's going to make us do some more for homework here.
No homework today. That's pretty nice. But yeah,
All
so
right.
the moisture load is the latent load. That's the hard one. I always like to remind people that's the hard one. The sensible load, cooling is easy, drying is hard. And those two loads make up what is called the total cooling load. And sometimes you'll hear a term called the sensible heat fraction, which is basically just the sensible load divided by the total load. And so a high sensible load, sensible heat fraction would be somewhere like out in, you know, the desert, Arizona. A low sensible heat fraction would be, you know, you're in the Gulf Coast, a lot of humidity. Anyway, and the coil matching, you know, that's what we were talking about earlier. You know, again, the indoor coil has been tested with that certain condensing unit. And I think we've also spent a good amount of time on this, that, you know, we design on the almost statistically hottest day of the summer. And you notice under that condition, we have 99 grains as our moisture load under that condition. And so that's what we're sizing our air conditioner for. But the reality is our peak moisture day is a third more moisture. That is a lot of grains, and it's on a day when it's not that hot. So again, it kind of gets into this need for, ultimately, I always try to build the case for, you know, variable speed or inverter driven or equipment that can adjust itself automatically is really, really critical. We also talked about this in a lot of our webinars, which is that basic, you know, here's a wall, here's a door, here's a window, there's a temperature difference across it. Each of those components has a different resistance to heat flow or a different U factor, same way of saying that. And there's heat gain or loss, in this case gain, through the walls, through the door, through the glass. And it's all based on this equation, UA delta T. So in this example, you do the math and you see the walls are contributing about 400 and the doors are about 200 and the windows are about 660, and that's about 1300 BTUs. So that's essentially what a load calc is doing, is it's going to do UA delta T under all those conditions. So now I want to get into it. Finally, we're into the good stuff here. What are we talking about? Well, ACCA, the Air Conditioning Contractors Association, have a process of calculating the load on the house called Manual J, and I'm sure many people have heard of it. And our goal is to kind of demo it and explain it and maybe make you feel a little more comfortable about what's in it and what affects it. So the load is from the house. The capacity is what you get from equipment. So equipment has capacity, houses have loads. So we want to, of course, design equipment to have enough capacity to satisfy the load without being too big. And so once you calculate the loads, then you're going to use what's called Manual S to select or size, or really I think specify equipment from a given manufacturer that is going to correctly satisfy the loads. And heating is pretty easy, and there's a lot of wiggle room on the sizing on heating. You want to be at least as big as the heating load. Cooling is a little more tricky, and there's a little different set of rules for if you're an air conditioner or if you're a heat pump. You can essentially upsize a heat pump a little bit more than a straight across the board air conditioner. So I thought I'd try to give an example, and Joey, you can grade me at the end and see how badly I bomb on this. But let's say that you do a load calc on a house and the summer cooling load is 28,000 BTUs an hour, okay? And of that, we'll break it down. We're gonna say that 22,000 is sensible and 6,000 is latent, and that would give you a sensible heat fraction of about 79%. Okay, so then you go to this manufacturer's line of equipment. You go, okay, we've got and everybody, that is itself is a nominal, most people would say that's a nominal, about a 2.5 ton air conditioner right here. Okay, so it's a 2.5 ton air conditioner because a ton is by definition 12,000 BTUs an hour. Joey, where does the term ton come from?
It has something to do with ice, if I recall correctly.
Exactly. A 2,000 pound block of ice melts at a rate of 12,000 BTUs an hour. So it comes from pre-refrigeration days. So our choices here, so, you know, you go, okay, that's about a 2.5 ton air conditioner. And so we look at this nominal 2.5 ton air conditioner. I say nominal because the manufacturer calls it their nominal 2.5 ton. I always think it's interesting in that they're lying because it doesn't actually do 2.5 tons. It only does 29,000 instead of 30,000. But anyway, this particular model will do 24,000 sensible, 5,000 latent, that's 29,000 total. That's bigger than 28,000. We're good to go, right? Except we're not, because what Manual S tells you is it's very important you put equipment in that has enough sensible capacity to satisfy the sensible load, 24 is greater than 22, and enough latent capacity to satisfy the latent load. We don't have it. So this equipment is not the right choice for this particular load. So then we go, okay, maybe I'll jump up to the nominal 3 ton system, which of course doesn't actually do 3 tons. It only does 35,000. And of that particular one, 29,000 is sensible and 6,000 is latent. Okay, so now we have enough latent capacity and we have more than enough sensible capacity. So you might say, okay, and you could say if these are our only 2 choices, option B is the right choice because it is enough capacity on latent and enough capacity on sensible. But you'll notice it's also oversized by a fairly significant amount. And you can do another check to see if your I think it's 15% oversizing that you're allowed, and we might be okay on that. So we have to do 35,000 divided by 28 and see if we're more than 1.15. I think we would be oversized. So we have a third option here, and this is another, and this might be just a different condensing unit and a different coil, but this particular one gives us 29,000 BTUs, but it gives us 22,000 sensible and 7,000 latent. So we have more than enough latent, and we have enough sensible, and we are slightly larger total, but that's okay. So option C would be the good system to install in this case. And again, I always, anytime I could err on the side of good extra latent, that's not a bad thing, because remember, our latent, load doesn't necessarily correspond with our hottest day. So that was enough said on that. I thought I'd share with you what the code says, which is the language right here. Basically select it or size it, select it with manual J and S. And what Georgia added was one sentence. We didn't modify anything, we just added a sentence. And what we said is, if you have automatically modulating capacity, heating or cooling, what does that mean? Equipment that can automatically adjust its output. You are deemed to comply, provided your system can throttle itself to be less than the peak load. So let me go back to this. If you put, let's say, a 4-ton variable speed air conditioner in, 4 tons is way bigger than that. But if that system can throttle down to 2 tons, then I would say that system is fine. So if anybody, a better choice would be a 3-ton unit that would throttle down to say 1.5 or something. But the idea being that as long as you put variable speed in, if it can automatically reduce itself to less than the peak load, I'm going to give you a little wiggle room, and that way there's no reason to fudge the manual J. Why do people fudge manual J? Because they think they want a bigger air conditioner than what they do. So we'll talk about that in a second. So Joey, what are the big things that factor into manual J?
I would guess location,
Meaning
orientation,
the weather of your city, right?
sure. Orientation, so solar orientation, where you put your windows on which side of the house is going to have a huge impact on your solar heat gain.
Yep.
The envelope, so your air barrier and your thermal barrier, so how well the home is insulated and how well it's air sealed. The ducts, if you have ducts in your system, same thing, if they're going to be losing heat through insulation or losing heat through air leakage, that's could impact your manual J.
Yep.
Internal gains, so this is people and also appliances in the home. And we'll see in the manual J that we actually perform later that it's actually pretty significant, more than you would probably think. And then ventilation, if you have any fans, bath fans, ERVs, ventilating dehumidifiers, etc.
You got it. And then I thought I'd throw this out. Manual J is all the joy of doing your taxes. So I hope that people got their taxes done yesterday. And if you filed an extension, good luck. So I thought I'd blow this up though just a little bit. This was what manual J used to look like a long time ago. And they still have this kind of spreadsheet version. And you'll notice when you say location, you put in your city and your state, and it has weather data, and it's using Atlanta Airport. And their numbers are slightly different from what I have. They're like 1 degree different on heating and cooling, but these are what's called the 1% design conditions. And there's your indoor design conditions. And then you're going to put in, essentially, you're going to describe your envelope, and we'll see this when we demo the software. So you've got windows and walls and doors and ceilings and floors and infiltration and internal gains and all that stuff. So talking about things in a little more detail, the definition of design temperature is statistical weather data, and it says if we monitor the outdoor temperature every hour of the summer, for example, in Atlanta, it only gets hotter than 92 or 91, depending on whose version you're talking about 1% of the hour. So, there's almost 8,800 hours in a year. If you assume the summer is let's make it 2,500 hours, let's say, arguably, I don't know, whatever it is. And 1% would be 25 hours out of the summer, the entire summer, only 25 hours would it actually get hotter than 91 or 92 degrees. That's the statistical data that sets our outdoor design condition. And same for the winter, only it's 99% of the time it's hotter than, in this case, 23 or 24 degrees, which is what Atlanta's design temperature is. And there's also indoor design temperatures, which are usually 70 and 75. I think I had that up here. But those, you are allowed to override heating and go to 72 if you should so choose. I think that's people in the northern climate. But you're not allowed to go lower than 75 on cooling. Okay, so what happens if we pick the winter condition? What we're basically doing is saying at nighttime, and Joey, why are we doing this at nighttime? Because what's not out at night? I don't know. I think Joey passed out. What's not out at night is the sun. That's okay. The comet. At nighttime, we have a certain, we have no solar gain. So that's why we calculate the heating load at nighttime. We have no solar gain, and we do effectively UA delta T, and there's the delta T, across the walls, the floors, the ceilings. We account for infiltration. We account for where the ducts are, a few other little things, and we completely ignore all the internal gains. So worst case, we are really a worst case load calc in the wintertime. So that's basically comes up with our winter load. Summer is the same thing, only going a different direction. Now the heat is gained into the building, and we're gaining 92 outside is our summer design, 75 inside. So there's UA delta T. There's a moisture condition we're trying to maintain on the inside as well. So it's not just temperature. Certain components like attics, they're going to be hotter. So there's a much bigger delta T across the ceiling, a vented attic. And we are accounting for internal gains, people, lights, appliances, and so on. So we do account for all that. And we basically can do what's called a room by room load calculation, where you calculate the heat loss or gain under this individual room, or we could do what's called a block load or a whole house load. And that's just a little faster. So that's the one I'm going to focus on today. So room by room is really important. I would generally say that's the way to do it, because once you do, you know the heating load on this room, you know the cooling load on this room, you can then size, you can use that information to size ductwork. So that's used for manual D. So for a duct design, if you don't know, if you just do a block load, it's better than nothing. What you can do is just sort of say, okay, well, this room is, you know, 150 square feet, and the total building is 1,500 square feet. So I'm going to put 10% of the supply air into there. It's a swag, but it's reasonable. So it's better than nothing. And then most of us today, of course, aren't going to do our taxes by hand. We're going to use Manual J software. And of course, Joey, just really quickly, why is sizing so important? You know, so I don't get drippy supplies.
That's definitely one reason. We tend to see equipment that's oversized, which causes the equipment to short cycle. So it'll run for a few minutes, then turn off, and then turn right back on again in 5 minutes. So it's just like stop and go traffic in your car. You know, it's just really not good for the equipment.
Yeah, yeah. And I think most people are tuned into that. And then just this was interesting. We just have been doing some work with Missouri, and they had participated in a study. They looked at over 80 homes, new homes, and they found this was this is a really beautiful bell curve, isn't it? Of the median oversized equipment was 1.5 tons. So you know, if you're on the 1.5, 2 tons too big, your systems are not able to throttle probably, and they are essentially not dealing with the moisture load very effectively. So hopefully everybody understands why this is so important. I would imagine we probably see a similar curve in Georgia. All right, Joey, what does this acronym GIGO mean?
You stumped me there, Mike.
I'm so sorry.
You get in what you get out?
Very close, yes. Garbage in equals garbage out. And so, sorry, I didn't mean to stump you. It's an old programming. You didn't learn to program in Fortran like I did? Are you serious? Wow. Your life is better for it. So anyway, it's an old term that basically says if you feed a computer basically the wrong inputs, whatever comes out is not terribly meaningful. And so that is probably the most common thing that we see with manual J. It's when there's problems with manual J, it's usually not the problem of the algorithms or the software. It's usually someone didn't use it right. And manual J is a tool. And if you use a tool incorrectly, you know, that's on you. And people do this both intentionally and unintentionally. So I think we're going to talk about what we call the usual suspects. And one of the reasons or advantages of a program like I'll pitch Earthcraft is that we require our technical advisors to not only collect the manual J, but to actually study it and look for problems on it. And so we train them, and they don't necessarily, you know, some of them probably do offer load calcs as part of their service, but they know enough about them to look for the problem areas and to kind of say, does this pass the straight face test? And I've seen people fudge pretty much everything on this list. And you kind of go, some of these, that was intentional. So don't mess with the design temperatures, and we'll go down this list. Okay. I would say too, wrong areas and wrong dimensions, that happens, and that may not be on purpose. That could be accidental, but I would say most of the other ones might be deliberate. So outdoor design conditions are when what we're saying is, you know, pick the default. Take what the software tells you to use. If you want to change it a degree or two, we can talk about that. But my comment is do everything by the default until you get to the very end. And if you get to the very end and your engineering experience tells you, okay, I'm going to make a slight adjustment on this, that's okay. But you know, don't go in the beginning and say, oh, you know, I remember that time it got to be 104 here in Atlanta, so I better use that as my design condition. So very typically, you just choose the city and you take those defaults. And some of the software allows you to pick which version of the design condition you want. The default for manual J version 8 is the 1% and 99%, meaning Henderson City, Kentucky, 1% of the time in the summer does it get hotter than 91 degrees. If you picked 0.4%, it would up the design temperature to 93 degrees. And likewise, their design winter temperature is 15 degrees. If you pick the 99.6%, you notice you drop another 8 degrees on the heating design side. So when you override these, that can have a big output outcome. So the other thing is, don't mess with the indoor design temperatures. You should just use 70 and 75. And I've seen people, like in this case, someone tried to slip something in. They made the indoor design temperature be 72 degrees. So they would have a 20-degree delta across it. And that's not something you're supposed to do. Orientation, this is a terrible graph for this because this building, when they rotated it, had almost no change in orientation, but somehow I'll show you one that has a little more impact. But when you enter information about windows in manual J, it's particularly good about taking into account the overhangs, and so the degree of shading. And the big three that matter are how big is the overhang, how tall is the window, and how close to the overhang is the window. So those X, Y, and H are data that you're going to typically enter. And then, of course, how many people are in the house. I may have told you the story, Joey, about the guy who brought me a load calc, and I did it, and I said, well, depending on assumptions, it's either 1.5 or 2 tons. And he started laughing, and he goes, well, somebody else did a load calc for me, and they said it was 3 tons. And I was like, oh man, maybe I screwed up. And I said, can I see theirs? And I looked at their inputs, and amongst other things, like Atlanta had a design temperature of 105. They had 15 people in a 3-bedroom house. So those are great examples of ways to fudge your results.
You don't know. They could have had 15 people in the house.
It could have been a party. So anyway, the other big thing is you want to, of course, try to get the shell description correct. And you know, if you assume, oh, this wall, I know it's insulated. If you're really conservative, you might say it's R11 versus R13. That's not going to be as big of a difference if you assume this wall is not insulated and it is insulated, that kind of thing. And also the windows, we really want to try to get the windows pretty close to right, because windows are a big impact on cooling. And lastly, the last big one is air leakage, which, you know, the cheesy way of doing air leakage is to sort of swag it with a highly technical guess of average, semi-tight, tight, yeah, feeling loosey, loosey-goosey, that kind of thing. The better software, I think, allows you to enter a blower door number. So you can enter a CFM 50 as a single point blower door test, or you can actually do a multi-point blower door test. I'm going to show you what that is. And you can get this coefficient and this exponent, and you can key those in. And that's actually the most accurate way to do that. I just thought I'd mention too that infiltration can be a big factor. So the sensible gain is, of course, the temperature difference times 1.08, 1.1. That should be a times instead of a decimal point right there. So it's CFM times 1.1 times temperature difference. That one's pretty easy. The latent gain has to do with, if you remember psychrometrics, how much differential in the grains between the indoor conditions and the outdoor conditions. And then that 0.68 and the 1.1 are just multipliers. So going back to the air leakage though, the software that we are using, if you were to do a multi-point blower door test and plot it just on regular graph paper, it would look like this. It's a weird curve that looks like this. But if you were to plot it on logarithmic paper, it would look like this. It would be a straight line. So, and you can, from this information, you can do a curve fit, or the software does a curve fit, and it tells you this, the value for C and the value for N. Okay, I know this is getting deep in the weeds. If you understand this, great. If you don't worry about it. But ultimately, I'm trying to show you our software, the one we're using is kind of weird. They allow you to enter a C and N, but they don't really help you otherwise. So I'm trying to help you. If you know what your CFM 50 is and you assume a default for N, you can back out what other value to see. And here's the magic equation when you do the math. So just take your blower door result, divide it by 12.715, and that gives you the number we're going to enter. And I'll show you that in a second. Okay, all right. I threw a lot at you. I just want to pause for a minute to see, does anybody have any questions? Because we're about to demo a problem. And is anyone still cognizant, awake, alert? I don't know. Joey, are you still awake, alert, Joey?
Awake, yes. Alert, questionable.
Questionable. Okay.
Yeah, it seems like everyone's here. We got a couple questions, but I think we can wait until the end to take them. They're not specific to any of. Yeah.
Okay, so what I thought I would do, and hopefully it's going to work, and I want to give credit for Joey. Wait, no, Joey, not yet, come back, Joey, come back. I want to set up the problem first. You got a little jumpy.
Okay.
Can you give it back to me for a sec? Okay, yes.
No, it's broken, sorry.
Oh, that's okay. So I want to set this problem up first, and then we're going to show you some software which is running on an iPad, which is not on my laptop. And Joey, to his credit, figured out how to make it work, which is, I'm going to let you explain that. That's more technical than anything else. But anyway, so manual J example, we're going to start off with we're going to do a fairly simple house, and we're going to do a block load on this house. So that's we're going to treat it as one big zone. And the basic takeoffs on this house, first thing we need to know is, where's the thermal envelope? That's this red line. It's got an attached garage. There's a door to the garage, a front door. There's an overhang porch, 4 feet. This is looking like the house I grew up in, I think. And there's a length of that red line, which is 54 feet and 54 feet on the bottom, and then 40 feet on that side and 40 feet on that side. So the whole line is 100, I can't even read my thing here, 188 feet. And the wall itself is 9 foot high. So the gross wall area is 1692. That's that red line times 9. And the floor area of the home would be the 3 boxes. So it'd be the laundry, 12 by 14, the kitchen and living area, which is 20 by 31, and the bedroom, which is 20 by 40, okay? And that adds up to be 1588 square feet. We're gonna have a flat ceiling, 1588 square feet. So this is a pretty simple house. And the windows on this house are distributed, as you can see. There's A windows that are, there's three different kinds of windows, just to be difficult, that are all double pane low E. So they're all pretty close to having the same performance. They add up to be 140. I don't know if we need that. And then there's also a glass door, sliding glass door, which is treated like a window. So we've got two sliding glass doors. Those we're going to say are just double pane, not low E, and they have a tint. So, you know, they're a U factor of that and a solar heat gain of that. And there's there's a front door and a door to the garage. So we'll account for those. That's my basic assumptions. And if I need the volume, it's just the floor area times the ceiling height. So to go a little deeper, some software, you would just enter the gross area of the exterior wall. And if there's different walls of different R values, you would break it apart. But our software is a little different. You enter the wall by orientation, and then you'll assign a window to that wall. So you have to kind of tell it, this blue line here is, you know, 20 feet times 9. So that's the right wall. And it's got, and we'll assign it two of these A windows, which will subtract out. And so you can see that we have 4 walls. The red wall is on the back, the black walls are on the left, and the green walls face front. And we're gonna say, just to keep the orientation simple, we're gonna say north is up, south is down, east is to the right, west is to the left. And I'll show you when we rotate. So right now we have a pretty good solar orientation, that we have a couple windows on the east, none on the west, and most of our glass is on the north with a little bit on, a fair amount on the south with some overhangs. So that's kind of how we're starting. And just while I'm at it, when I talk about I'm going to assume a 1 foot overhang everywhere except for the porch. So the C windows are 4050 windows, so they're 5 foot tall. And we're going to assume there's a 2 foot distance there and probably a 2 foot distance here. That makes it 9, and a 4 foot overhang. So there's my information that I have to key in, and I'll do the same for each of the other windows as well. So Joey, is this making sense to you? You're my test on this. So far, so good?
So far, so good.
Okay, now I really loaded up this slide. I just decided to put everything on one screen. So what's new on this slide is I'm going to show you how I got my blower door number. So I decided to assume that this is built to code today. So I'm going to go with a 5 ACH 50. I know the volume, I know 60. I can back out the CFM 50, and the answer is almost 1200. I can't read, I think it's 1191. Then I'm going to use my magic equation and back out the value for the coefficient, which is divided by 12.715. And I get a value of C of 93.7, and an N is that. And again, don't worry about what those mean, just roll with it. But I'm going to enter those into the software, and that means basically I've got this blower door result. Other things, I'm going to assume that the walls are 2x4. There's R13. It's just standard wall with wood siding or something. R38 flat ceiling, R19. I'm going to just do a vented crawl space to keep it simple. I'm going to put the ducts in the attic with R8, and I'm going to assume 6% duct leakage, which is Georgia's code. And I'm going to do a ventilation calculation. We did this, Joey, back in our other webinars. We talked about this. This is about a 1,600 square foot house. So I'm going to add 16 CFM plus people times 7.5. This is a 2-bedroom house, so we're going to assume 3 people. 3 times 7.5 is, I think, is 22.5. Add that to the 16. That's how I got that number. So I'm going to enter that in, and I think now, Joey, now it's time. It's time. Let's jump over. Okay. So while you're making good stuff happen, right? We there?
Yep, you should be seeing it, I hope.
I'm not seeing it. Oh, maybe it's just because I can't see it.
No,
I'll tell you what, Joey, you can see it. I'm going to move. You can see me moving. Is that right?
Yep.
Okay,
Well, it's confirmed. Thank you, everyone. And we do know, as Mike kind of alluded to, this took a little bit of yeah. So it is a little bit blurry. We apologize, but I think Mike's going to do a good job of reading everything out to you. So
So first of all, I'm starting in the software. This is made for an iPad. It's called HVAC Res J or something really boring like that. Probably an engineer came up with the title. But anyway, this is my house. It's called, this is my list of projects. But anyway, this one is called Simple House. And you can see that it's got 1588 square feet. I'm gonna move that around so you can see it. It's got a 9-foot ceiling. It's 2 bedrooms, 3 occupants, and I'm assuming my appliance load down at the bottom is pretty typical. I'm just gonna say medium. So that's essentially the kitchen and the fridge and all that stuff. You can go more in depth on that if you want. A couple other basic things about it before I go into it. Here's the set points. You can see 75 and 70. You can see 50% relative humidity, and don't worry about some of that other stuff. Construction tightness, that actually is kind of disabled at the moment because I'm doing infiltration via blower door. So I'm entering in C is 94, 93.7, and N is that. And so I've told it that, sorry, I was gonna translated, that means the software takes that, it calculates a natural cooling air changes of 0.22, or it backs out about 53 CFM. That's the impact of the house leakage on the cooling load is 53 CFM of outside air. On the heating load, the heating one, it's the same information input. And you can see it says, okay, that's about 0.41 natural air changes in the winter. And that's close to 100 CFM impact because of air leakage. So that's used to calculate the impact of the leakage of the house. For ducts, I'm using a pretty basic assumption of a single zone system located in the attic. It says unvented attic. It's actually not. It's a vented attic. 1 story. Here's the duct insulation is R8, 6% duct leakage. Based on the floor area and these assumptions, it's guesstimating about 429 square feet of duct surface area, that's supply ducts in the attic. And then also for the return, it's guesstimating about 79 square feet of return ducts. So this is just defaults. You can override them. You can make some of the ducts be in the house, etc. But that's essentially my inputs on that. And I think that's all I want to show here. So when I want to get into the project, I'm going to hit the envelope tab. And the envelope tab is where I see my opaque surfaces. So there's the front wall there, and I've named it. I always recommend you name things intelligently. I tried to name it above grade wall front, so I know this is front. And you'll see at the moment it's facing south. The construction type of that wall is a wood frame. There's a huge spinner wheel here of 1,000 choices. This is welcome to Manual J. And after a while, you kind of learn that, oh, a 12B is an R11 and a 12C is an R13. So I'm going to pick this 12C that has wood frame wall, not metal frame, wood frame wall, and it's an R13 in the cavity. There's no insulation board in its siding. That's a U factor of 0.091. That's pretty good. That seems reasonable. I'm going to accept that. And also I'm going to, and in there it says my U factor, and I'm going to tell it my wall is 54 feet by 9 feet. So you don't actually enter areas on walls. You just tell it the dimensions for this software. And I'll do the same thing and I'll copy that and it'll be the right wall. And then I'll adjust things and change the orientation and the back wall and so on. I'm going to enter a floor over the crawl space. So, that was my description is this is a floor. You can see it's an R19. They call it blanket. They mean a bat, and pretty standard there. Oh, and then of course the floor area of the house, the actual floor area is 1588, but I can't enter that. So I have to divide it by say 40 and then enter 39.7 times 40 will give me 1588. So you got to kind of trick it, which is silly. The ceiling is the same thing, only here I picked a R38 ceiling, and you can see all the choices in here. Now I've lost it again. Okay, without a radiant barrier. And again, you learn after a while the codes, like a 16 means a ceiling and a 19 means a floor, things like that. So we've entered the opaque areas. Also on this one, you enter opaque doors as well. So here's my front door, It's a wood or metal door. It's associated with above grade wall front. So yeah, that's right. So it's going to subtract, you know, that 21 square feet that I'm telling it, 3 by 7. It's going to subtract that out of the front wall area. And it's an R3, so I just put a U factor there. So there's the construction I chose. And I forgot to enter my garage door, so I'll do that. So I'm going to hit plus, copy from, I'm going to copy something similar. In this case, I'm going to copy the front door, hit save. And now I'm going to go up here and I'm going to edit it. And I'm going to change it to something intelligent, hopefully. And everything is correct. It's the right R value, it's the right area, but it's not in the right wall. So I want to say this one should be in the left wall. So you get the, hopefully you get the idea of how you do all this. Joey, are you still awake? You're still there?
I'm still awake. I do want to point out on the screen too, because I mentioned earlier about the internal gains.
Yes.
You can see, you know, there's what, 3,600 BTUs just from internal gains.
And a lot of that comes, sorry, I was going to show you where that comes from. Appliance load down here at the bottom. Do you see that? So I can change that to low, and you'll notice that the internal gains dropped. So that's medium is, you know, I think medium's a little bit on the high. It depends. Who knows? Who knows? Let's just go with that at this point. But yes, sorry, I didn't mean to cut you off. Were you gonna say anything else?
No, that's okay. And two, I just wanted to mention that I'm restarting the sharing. It seems like a few people are having trouble. The common denominator seems that they are on a browser. So I would encourage you next time to download the GoToWebinar software, and that you should be able to see it at that point.
Okay, apologies. We are going to do, I just have a couple other quick things I want to show you, which is I'm going to show you Windows over here. And did I keep my door in there? Something like that, yeah. I changed something, I'm not sure what I did, but my windows, my front A windows are attached to wall A, as you can see up there. They're a certain construction type, double pane window operable. It's got a low E coating on surface 2. That it really doesn't matter what that is, because ultimately what matters is the U value and the solar heat gain. But I try to put something descriptive in, and each of those windows is 12 square feet, and there are 2 of them. So the only other comment would be down here in the lower right corner is where I give it information about the overhang and the distance, and there's not much impact from that overhang on that window. But if I go to window C, which is also in wall A, then you can see it's got different performance, but ultimately it's got a significant overhang here. It's a 4-foot overhang, 5-foot window, 2 foot between the top of the window and the bottom of the overhang. And I usually take defaults for things like internal blinds and stuff like that. Some people, if you want to make it worst case, you just assume no blinds, but that doesn't seem terribly reasonable. So again, you'll enter all the glass on here. And if you're not seeing this, don't worry, I'm just about done. And I've made some slight change on here because my number is not quite adding up to what it should be or what it was before, but it's pretty close. So what else did I want to show? I can look at, go back to project. I can look at the cooling load breakdown. That's what you're seeing here. The total cooling load is about 22,400. The heating load is about almost 30,000. And then this is the AED curve, and I'm going to explain that in a sec. I have to hit calculate, sorry. There's the AED curve. Suffice it to say that we are within the limit of the AED curve, and I'll explain it in just a second. Is there anything else I want to show? You can also, I could do reports that have that same information. Here's the summary of it that shows this is about 1.9 tons, about 30,000 on heating, and I can go deeper and I can see that there's the sensible cooling load up here towards the top, and then there's the latent load underneath, and I can do, you know, a little bit more. Okay, so Joey, I think I'm ready to say that was our demo. Now let's show some results.
Okay, just real quick, there are a couple people asking. The software he's using is HVAC Load Plus.
No,
and it's by
Carmel.
Oh, sorry.
I
Yeah, it's
think,
by Carmel.
yeah, I think they have a different name for the PC version. I think it's called
Okay.
Res Load, HVAC Res Load. But just go to their, that's the manufacturer. Yeah, so
Yeah, and you want to make sure that you find one that's approved. It looks like there's some bogus apps on the App Store, so make sure that you go to the ACCA website. They're going to have a list of approved software. RightSoft obviously is the big one. The one that we're
right.
using is this one,
Yeah, we
CarmelSoft.
have RightSoft at Southface as well. This one just seemed easier to do for me for this. So Joey, am I back?
I'm going to give it to you right now.
Okay, show my screen.
All right.
I just want to make sure we finish on time. So I thought I'd show you what happens based on orientation. So I made some slight tweak a minute ago, so my number's not quite the same, but my base load was about 22,400, and you can see the sensible was 20,300. Are y'all seeing this, Joey?
Yep,
Everything
we
good?
got it.
So here's my base load, almost 30,000 heating. If I rotate the building 45 degrees, now the front faces southwest, you can see that we're picking up load. We're a little bit more sensible. And then if I face due west, this is my worst case load in this example. The front faces west, the back faces east, and this is not good from a sort of solar gain standpoint. If I rotate northwest, I'm still in not great situation here. Northwest and southwest are almost comparable. When I'm north, I'm at my best orientation. It's a little better than south. South is a little bit. So in this case, the more glass, when the front faces north, more glass is actually facing south. The glass side of the house is facing south for this particular example. When I rotate northeast, the front facing northeast, my load is almost at peak again. And as is when it's facing east, it's almost at peak again. So if the front faces east or west, that's pretty bad. And you'll notice too, I also failed my AED curve, and I'll explain what adequate exposure diversity is on the next slide. And then I rotate back. So that, I just kind of wanted to show you the sensitivity to the orientation on this pretty simple house with not a lot of glass, and frankly, pretty good glass. So we had, except for the sliding glass door, we had pretty decent glass. And so that's the basic variation. And we saw a difference of about 4,000 BTUs between the best and the worst orientation. So that's a third of a ton right there on this particular very simple. If that glass was clear or single pane, it would be much, much more extreme on this. So or a lot more glass, that would also be a factor. So let's explain adequate exposure diversity. I put this slide so people can read it on their own, but basically there's a sort of an average load approach, which is what we have been using. And there's also a check that you do that says, what is the load on the house every hour between 8 a.m. and 8 p.m.? And if your peak at a given hour of the day is more than 30% above your average, then you're you've exceeded your AED, you're sort of out of range, if you will. And so the basic assumption here is, so when the front faces south, you can see we're well below our 30% line here of forgiveness. And when a front faces northeast, we have a couple hours of the day, about 2 p.m. to about 5 p.m., when the gain on the house, because of the orientation and the sun angle, is outside of whack. So what we would do essentially is just add in a little extra BTUs to our load to account for that. And you do this thing called a peak load procedure. So I think hopefully that explains it. If your house has a reasonable amount of glass, reasonably dispersed, you chances are never going to exceed this. But my example, there's no glass on one side, so depending on how that side is oriented, that could have a big swing. Okay, that was enough said. I'm terribly excited that we talked about that. The last thing I wanted to show you is the impact of house air leakage, and just basically say when you're at 5 ACH 50, that was our base case. If I make it a little tighter, like to what the code should be in Georgia, 3 ACH 50, you can see our cooling load drops a little bit. Our heating load, dropped 3,000 BTUs. So a decent swing, but you can also see if we are twice as leaky. We're at 10 ACH 50. You can see there's a much bigger swing. And if we're at 15 ACH 50, that was a, look at the jump here. We went from about 30,000 to 44,000. So a big impact on heating and about 6,000 BTUs an hour on cooling. So that's about a half a ton on cooling. So air leakage is a big impact on your load, in particular your heating, but also particularly on your latent load. That's the key thing here. A tight house is a good thing because it helps control the infiltration impact of moisture. So that's the big thing I wanted to show. Joey, what did I miss when I said all that?
Oh, nothing that I can think of.
Okay, I was trying to ramble to get to the finish line on time. So just trying to show you that a couple things you can play with on a load. Again, appreciate that a load calc is not an energy model. It's a heat calculation at 1 hour of the hottest day, or in this case, the hottest day of the year, a couple hours out of the day. It's not the same as an energy model, which would do that same calculation basically every hour of the year. Anything you want to add on this? We have another webinar. Hopefully this was helpful for you. I'm hoping we have some good comments. If you can stick around and hang out for the comments. I'm still showing some people are still awake.
Yeah,
and we also, we also have green prints. Again, a plug for green prints. All right, Joey, hit me.
Yeah. Well, so I don't want to say if this is your first time, what we usually do is kind of sort of close down at 12, and then we hang around for a little while to ask questions. We've got a handful of questions, so we'll start moving through those. If you have a question that you want us to answer, go ahead and start shooting those in. I'll just reiterate what Mike said. We'll do this thing around the same time next month. We'll talk about high performance design, which is going to be a lot of fun. And we also have just a veritable load of previous webinars. Obviously, we referenced quite a few of them. You can find those on our YouTube page. You can also just find them on our website, and you'll basically see the recording of those. So
I was going to try to pull those up, and there they are.
At least one person's still awake.
Oh, good.
So it looks like, do you have preferred software? You just said you use that one because we had it.
Oh, that's a great question. I would say the most common ones are, I think it's Elite makes it, and RightSoft is probably the one that most people in industry use, and they have ones that can do drawings. And the most time-consuming part of a load calc is just getting all the takeoff information and slamming it into the software. So some of them have a thing where you can just sort of scan in your floor plans and just do a quick sketch with the tool, and then it knows the walls, and you go in and edit things and stuff like that. And RightSoft also has a new version for a tablet or a cell phone, which is pretty cool. And this one is nice because it's cheap. So this is we were asked. I don't know how they price out, but there are other load calcs that you can do. They're not necessarily ACCA approved. That doesn't mean they're wrong or they're incorrect, but if you're doing it for a program, it probably needs to be ACCA approved. So I would just say go to ACCA's website and see what they say. Good question. I've used most of them, and I don't have any great preference for one over the other. I think for a block load, this was fine. I would say for a room by room, this one's a little bit clunky. You can do it, but it's a little bit more clunky. But it's probably one of those things where if you use it enough, you get pretty good at it.
All right, I'm trying to read through the questions. Let me shoot you with an easier one.
Oh, I like easy.
We talked about ACCA and the design temperatures based on basically historical data. Are they moving those up any based on temperatures?
Yeah.
And increasing.
I don't know where that slide is. Right here. Yes, they are. But it's a 30-year running average. I thought that was on one of the slides. It's a 30-year average, so you're not don't expect a whole lot of change. And honestly, I don't care if it's 91 or 92. I might even, It depends on what it's for. I might even say, okay, you can even go to, you know, 95 degrees. That's the upper limit. I think I'm gonna wave my red flag in a big way if you're using a design temperature that's much hotter than that. But I've seen people turn in loads that did that. Commercial buildings, a lot of mechanical engineers, sometimes they will hit it with a sledgehammer, and they'll use the 99.6 and the 0.4 design temperatures, which I had up a second ago. No, not that one.
And this question here is not a plant. Does Southface offer any load calc classes?
Services. Oh, classes. Oh.
And we had a question about services as well, actually.
I'll say yes to some extent on both of those. If we have enough interest, I would be happy to offer a class. I have, like I said, somewhere developed teaching a class on that. So yeah, if I would say we're happy to do that. The one thing about a class though is we probably have to pick a software and go with it.
And then everyone's gonna have to purchase it.
Right, because I might be tempted to use the one we just did because it was cheaper. But you know, if you're a power user of this, you might want to go with. Although I will say, I had to learn. I picked up the book. This is a long time ago. I learned WriteSoft when it was a DOS-based version. How old is that? This is back in the 90s, and it was ugly. But I kind of slogged my way through a load or two, and then you kind of get it down. So I think once you learn one, it's pretty easy to jump over and use somebody else's. So, and yes, I think we occasionally do offer load calc services. It kind of depends on how busy we are and our available resources. So, yeah. So yes, I have done them occasionally, and so have others at Southface, because it's probably not going to be me doing it.
So there's a home builder who wants to know if they should just go ahead and develop the expertise to do manual J's, or should they rely on their HVAC contractor?
I love the idea of home builder educating themselves and learning how to do this. And I want to say it is doable. Home builders have to master so much stuff that is, to me, more complicated than this. You know, understanding payroll and, you know, mortgage financing and all this stuff. So yeah, I think if you're a builder, you're a lot smarter than me, and you can absolutely pick this up. And that might be fun to teach a class for, you know, maybe the targeted people in the class are non-HVAC folks, although HVAC folks I think would benefit as well. So yeah, I think that's great. And I mean, again, I don't know how much this software is, but if you can pick it up for a couple $100 and you can learn it and do your own loads, and why not? Yeah, I think that's excellent.
Alrighty, there's someone, we talked a little bit about variable speed drives in the beginning. Can you clarify, are you talking just about the fan speed or also the compressor?
Yes. Where was that? Let's see. So I guess we'll just use this one. So the easy upgrade on any system today is this blower motor. And today, for example, and ECM motors, I'm not an expert on this, but ECM motors are, they have more than one way of controlling them, and there's sort of the cheap way, and then the more expensive but a little more feature way. Today, I believe any furnace you buy inherently comes with an ECM blower today, but not necessarily every heat pump you buy. So that's the easy thing to do, is to get an ECM blower, and the variable speed blower with a thermostat that can sort of smartly adjust it. Or if it doesn't have that feature, like my furnace is a condensing furnace. It came with an ECM motor. And what it does is it runs a little ramp up and ramp down approach. So when you first start it, it just doesn't blast the air. And when it's all satisfies the thermostat, it doesn't just run, shut off. So it kind of ramps up, ramps down, and that's like the default. But there are smarter controls that can, you know, sort of respond to what's actually the conditions are in the house. And those are usually linked to a much more variable speed compressor, as well as variable speed blower. You know, like I know Carrier has I can't think of the name of it, but a lot of manufacturers, you know, have this variable capability. And so in general, what we're looking for is equipment that can both adjust its blower speed and its capacity. And so that usually means the compressor as well. And so the higher SEER equipment, the better quality variable speed stuff is not just the blower, it's also the compressor.
Mm-hmm.
I don't know if I rambled on too much with that one, but you know, if people ask me today, what are the features I want, you know, it's like, yeah, you want variable speed. And that's why like the mini splits are so typically performing really well, because they're almost always inverter driven and can vary their load. The idea is to run a lot, but on low speed. You get good moisture control.
Yeah. There's no certification to perform a load calculation, is there?
I think I had that on the slide.
Eager folks in the audience here.
I thought I had that on one of these slides. Yeah, so load calcs are required by code. There are no details about who is qualified to perform them. And what do you turn in for code compliance? Depends on the jurisdiction. Yeah. Oh yeah, trust me, I did a load. And that's what's wrong with this. Now, and we do have some jurisdictions in Georgia that actually do require, they want a summary sheet of the load calc. But again, does the person that accepts that, do they actually look at it? So I would say that's better than nothing, because there's a certain amount of kind of liability if you turn in a sheet of paper and, you know, you fudged all the numbers on it, then, but to me, and Joey, am I still sharing? I think I had this up. Yeah, I had a load calc from a project, and I'm not going to go into it, but this they submitted, this is RightSoft, and they submitted all 31 pages of the report, because this is a room by room load calc, and it breaks down in a whole lot of ways, and I was just trying to kind of show this. So there's several reports, and this is actually the individual report for literally each room in the house. So there's the hall, there's the kitchen, there's the so on. And then I was going to show you, I'm going a little further. There's the AED curve right here for that particular house, and you can see it did okay. So there's a lot of forms to kind of present the same information. You know, here's the tax credit version of the form. So you know, today with computers, it's not a big deal. Just print all the, print them all as a PDF and send the report. But this is the kind of stuff that someone knowledgeable can check and look for things like, does this make sense? And I was going to see, let's check our design conditions and see if they did this right. This is for Athens. And so their outdoor design temperature for Athens is 27 degrees in the winter. It's a little bit warmer than Atlanta. And so is their cooling design temperature. It's close enough. It looks good to me. Their indoor design temperatures look good. You can see the delta T's created. All of this looks pretty decent to me. And here's the moisture in grains you can get. So yeah, those look like pretty good inputs. You can also do things like check the areas of the houses, and does anything look way out of whack here? You know, the biggest room in this house is the living room. The next biggest is the kitchen and some of the bedrooms. Those make sense. Yeah, this is a pretty small house, it looks like. So yeah, I think if you are trying to make sure it's done right, ask for a copy of the load calc, and if you're a code jurisdiction, ask for a summary sheet at the very least. And you know, put a little onus on it. Let them know that, and maybe spot check one. Maybe even hire somebody to spot check 1 in 100, something like that. That would be a great thing.
All right.
I can't gauge your excitement level, Joey. I can't gauge it.
Yes, sorry. Yeah. So that's 15 minutes or so. Questions.
Any other questions?
Trickling. Yeah, there are some more questions. Some of them are pretty specific. So Mike, if we can get to that last slide, it has both of our emails. You can send us a question. We'll try to answer it. Make sure you get the answer that you need without us, stumbling through it here on the.
Well, and
this
also too, we've got August 20th peg out, assuming that we both still have jobs in September. I have some ideas, but give us some thoughts if there's topics you'd like us to cover. And I would say your feedback is really valuable to us. So if there's topics that, if you want us to teach a class in how to do load calcs, then send that in. Let us know, because we want to be responsive. And if we have enough people, we'll do it. If we can get a sponsor, we do it for free, Joey. That'd be even better. That would be a more long-winded class than 1 hour of just you and me rattling on. So that would be, there'd be a punishing factor to that. But anything else we want to mention? Join us again in a month. And thank you so much for the great comments. And looking forward to your feedback. Joey, anything from your end?
Yeah, you can actually join us again in about 2 weeks and come to Green Prints.
Oh, yes.
So once again, if we can get to that slide, just go to our website. It's the first thing that pops up. Again, I think the admission for a virtual conference seems very reasonable based on some of the ones that I've been invited to. So definitely take advantage of that.
And also, it helps to stay afloat. So look at it as a donation to Mike and Joey staying in business, staying alive. So
yeah, make sure you put that memo on the check too.
Love it. Thanks, everybody. Really appreciate it. I hope you enjoyed it, and we look forward to your feedback. Thanks again.